Recently, we witnessed something that none of us were expecting. We witnessed the supermassive black hole that is at the center of our galaxy. Sounds close, right? But it is so far that you can't even see it with your naked eye. It is only the second black hole that we have discovered yet, and it came out after years of work. But the results were worth the wait, now that we have the image of two black holes. Now we can compare these two black holes and see what are the differences and similarities in both of them. Welcome to another video of Cosmos Observer, the only destination for your space curiosities. Now the question arises, how did they pull it off? And what exactly are we looking at? To begin with, how did they create these black hole images? First and foremost, they were not created by visible light. Radio waves with a wavelength of 1.3 millimeters were used to create them. All of the observations were made with radio telescopes, which resemble large satellite dishes. When a source releases radio waves, they travel radially in all directions, but since Earth is so far away, the wavefronts are almost perfectly flat and parallel by the time they reach our planet. A plane wave is what this is called. A radio telescope works by scanning the sky back and forth. It produces a bright spot when pointed directly at a radio source. Because all of the radio waves travel the same distance, bounce off the dish, and are received at the same time, they are in phase, meaning peaks and troughs line up. They interfere constructively. As the telescope approaches closer to the source, certain radio waves travel further than others, causing them to collide out of phase, causing destructive interference, and reducing the signal's intensity to zero. To get a sharp image, you want this drop down to be as steep as possible, such that the telescope generates peak intensity only when focused directly at the source, and then the intensity declines fast when the dish is moved even a fraction of an inch in any direction. These are two options for accomplishing this. One method is to look for radio waves with a higher frequency. As a result, even minor telescope movement represents a larger fraction of a wavelength. As a result, detrimental interference occurs more frequently. The other option is to extend the telescope's diameter, which increases the path length difference between radio waves on opposite sides of the telescope for a given angular adjustment. You can think of it as the size of the telescope's sensitive patch on the sky. It's proportional to wavelength and inversely proportional to telescope diameter. The difficulty in photographing a black hole is that the structure is visible only in a small area of the sky. Consider scanning the center of a black hole with a radio telescope. As the telescope goes over the left edge, you should see a bright spot, then a dark spot, and then another bright spot as it travels over the right edge. The issue is that the angular resolution of any particular radio telescope on Earth is far too high. As it passes through the black hole, it will continue to receive radio signals from the left side before switching to the right side. The resolution isn't significant enough to identify if the black hole has a ring structure or is just a blob. Observing at shorter wavelengths isn't possible because that light is obscured by our atmosphere or the material surrounding the black hole. If you want to improve resolution, the only method to do so is to increase the telescope's diameter. However, if you do the math, you'll see that seeing the ring of a black hole would require a telescope the size of the Earth, which is obviously impossible. But there is a technique to achieve something nearly as good. You don't need an entire dish the size of the Earth, merely bits of it will suffice, separated by up to the diameter of the Earth individual radio telescopes. You acquire the constructive and destructive interference required to attain the same angular resolution as an Earth-sized dish, as long as you can properly integrate the signals from all these faraway telescopes. Very long baseline interferometry is the name of this technology. As a result, the Event Horizon Telescope is a global network of radio observatories rather than a single telescope. Sagittarius A is being observed by all these telescopes at the same time. You can't bounce all the radio signals to a central receiver and add them up in real time like you can with a single telescope. Instead, each telescope records the signal at its precise location, as well as the time to the femtosecond. There are petabytes of data produced. But now that data has to be combined, the quickest way to do it was to transport hard drives as hand luggage to centralized locations. Now there is an additional problem. Every pair of telescopes give a different image, and combining the data is not that easy, as a source could be at any wavelength. To get one image, you would have to combine the image from every pair of telescopes, and it is no easy task. It does sound easy because I made it that way, but in reality, they weren't even images. They were just patterns of fringes. some wide and some narrow. By combining these patterns, we got the image that we have. Now the question is, what are we seeing? We all know that light can't escape a black hole, but what if it goes a little far from the event horizon? Well, a little won't make it as space and time are bending near the black hole. You must travel 2.6 radii away from the black hole to get a parallel beam that does not end up back in the black hole. If a light ray approaches from a distance of 2.6 Schwarzschild radii, it will only brush the photon sphere at its closest approach before continuing on to infinity. As a result, the resulting shadow looks more significant than the size of the black hole. Its size is 2.6 times that of the event horizon. And you can ask, what exactly are we looking at here? What is this shadow exactly? The event horizon is right in the middle of it. It corresponds to the shadow's center fairly well. Indeed, the entire backside of the event horizon is projected onto a ring on this shadow. So when we look at the black hole from one point in space, we can view the complete event horizon of the black hole. Maybe it's funny to talk about seeing it because it's entirely black, but that's exactly where the points on the shadow would map to. It gets weirder, since light can enter and travel around the back before being absorbed in the front, resulting in another image of the entire horizon in another annular ring. Then there was another one and another one after that. As you go closer to the edge of this shadow, you get virtually limitless representations of the event horizon. So what's the first light we notice? It's those light rays that enter at precisely the right angle to brush the photon sphere and eventually end up at our telescopes, casting a shadow 2.6 times the size of the event horizon. So this is essentially what we'd see if we were gazing perpendicular to the accretion disk, but we're more likely to be looking at the accretion disk from some random angle. We might even be peering over the edge. Do we observe the shadow of the black hole in that case? You might assume we wouldn't see the back of the accretion disk, but the truth is that we do because of the black hole's ability to distort space-time and bend light rays. The way it works is that light beams from the accretion disk bend over the top and reach our telescopes. As a result, we get something that looks like the image we get. Similarly, light from the accretion disk's bottom comes underneath, bends beneath the black hole, and travels towards us in this manner. And it's here that we obtain an image that resembles the black hole. That was used in the Interstellar movie. How funny is it that it is almost defying the laws of physics, and we are able to see the back and front of it at the same time? This was how we made the images of a black hole. I know there was a lot of science involved in this, but I hope I gave you digestible information. Let's now sit back and see what more we can get out of this black hole. Well, joke's on me, as once something goes inside, it won't get out.